So first thing I want to talk about today is reaction rates. Now reactions occur at several different rates. Some go very quickly, for an example an explosion, and some reactions go very slowly, something like rusting. As it turns out, something exploding and something rusting are the same type of reaction. They just happen to be the same type of reaction that occurs at a very different pace. So just be aware that we have fast and slow reactions. Now, the rate of a reaction is actually controlled by three primary factors. We've got concentration, we've got temperature, and we've got the structure of the molecules and the orientation of those molecules when they collide. Now we're going to look at each of these separately and take a look at the effect that each of them have on the rate of a reaction. So let's look first at concentration. Now reactions require collisions in order to occur. Now what those collisions do is they cause bonds to be broken, and a collision also has to happen in order for bonds to form. Molecules or atoms have to get close enough in order for those bonds to form. Now the higher the concentration, the more collisions you're going to have. And the more collisions you have, the faster the rate's going to be. So as concentration increases, reaction rate will increase. Let's take a look at temperature. Now with temperature, we know that collisions are needed to break and form bonds. Now the faster that molecules are moving, the more likely that they are to collide. And so the more they collide, the more likely they are to break a bond. So the higher the temperature, the faster molecules move, and the more they collide. So as temperature increases, reaction rate increases as well. Now if we look at orientation, when we talk about orientation, we're referring to the relative positioning in space of the molecules involved in a collision. There's a lot of molecules that require a very specific orientation during the collision in order to break or form the specific bonds needed for a particular reaction. So what that means is that not every collision between two molecules will in fact cause a reaction. Actually, most collisions that happen do not cause a reaction. Only the ones with the proper orientation based on the structure of those molecules will actually cause a reaction to happen. We can look at kind of a diagram of that. Some collisions have what we would say a very high orientation requirement, where there's a very specific place on that molecule where the collision has to occur. Some have a very low orientation requirement. So here we see a reaction. I wouldn't say if this is a high or a low. This is probably kind of a low reaction requirement. But we see that fluorine ion coming in. It hits that carbon atom between the hydrogens there. It causes that carbon-chlorine bond to break, and it causes the carbon-fluorine bond to form. And now rather than methyl chloride, we have methyl fluoride and a chloride ion. So as I mentioned in the previous slide there, most collisions occur without the proper orientation. If this fluorine atom were to hit maybe here, or collide with the hydrogen, or collide with the chlorine, it wouldn't actually be able to break that bond between the carbon and the chlorine. What has to happen is that fluorine atom has to collide with that carbon atom directly on the back side of that carbon chlorine bond in order to break it and then form that chlorine-fluorine bond. So this reaction does have an orientation requirement. It really is dependent upon the orientation of that fluorine-carbon collision. Let's take another look at reaction rate and how we might express it. Now, anytime we're looking at the rate of something, generally what's implied is some sort of progress measured by some unit of time. For example, when you're driving down the road, you have a speed, and that speed is really a distance rate. How many miles per hour are you traveling? And we just say miles per hour quite loosely without maybe thinking about what it really means. Now, for a chemical reaction, what we want to look at changing with time is something's concentration. It can be either a product or a reactant. So let's take a look at a reaction here where we've got a couple of iron ions reacting with a tin ion, and we're exchanging some electrons, and things are changing their charges there. Now, we're not going to really worry quite so much about the reaction itself, other than just some of the details from the reaction itself. So we start the reaction, and we're going to take a sample after 38.5 seconds. And what we see is we measured a product here. We measured iron 2+, and we see that it has a concentration of 0.0010 molar. Now, what we can assume is that when the reaction started, that concentration was in fact 0. So we're going to look at the rate of the reaction as the rate of iron 2+ formation. And so that would be expressed as the change in the concentration of iron 2+ over the change in time. Well, the change in the concentration of the iron 2+ was 0.001 minus 0, because it started at 0. And that change took 38.5 seconds. So the rate of appearance of the iron 2+ was 2.6 times 10 to the minus 5 molarity per second, or molar per second. And that's a very common rate unit for a reaction. It may be molar per minute or molar per hour, but molar per second is also frequently seen. So in that example, we showed the reaction as a rate of appearance of a product. We can also express the rate as a disappearance of reactants. So really, if we think about it, we know that the iron 2+ can only appear as quickly as the iron 3+ disappears. So the change in the iron 3 concentration with time would be the exact same rate as the iron 2+ in this reaction. Only here we would use a negative sign to indicate that the rate was decreasing because the concentration is going down. So the change in the iron concentration, or iron 3+ concentration, was actually a negative rate because the concentration was going down. Just like in a car, if you were braking, you would express the speed as a negative speed since speed was going down. We see here a graph where we show a reaction of H2 plus I2 going to 2HI, and we have our HI concentration increasing. So this is our red line here, and we're measuring just a rate right here, measuring a change in time, and we have a change in concentration on the y-axis there. If we want to measure one of the products here in green, or one of the reactants rather, we would see that its concentration is dropping with time, and so it has a negative concentration, or a negative rate rather. Now, we saw in that last example that we had a slightly different stoichiometry between the tin and the iron. And if we measured the rate of change in the concentration of the tin, we would have seen a different reaction rate based on what we measured. So the tin would have a different change in concentration than the iron did because it was being used up at a different rate based on the stoichiometry of the reaction. But what we want to make sure that we do is, when we say this is the reaction rate, we want to make sure that we are expressing the same value for the rate, and it doesn't matter which reactant or which product we are actually using. We should get the exact same rate for the reaction regardless of which component we're expressing it as. So what we want to do is we want to find a way to indicate how each component changes relative to its stoichiometry. So the first thing we're going to do is we notice that the iron here and the iron here both have a 1/2 coefficient in front of it. And that's because their coefficient in the balanced reaction is a 2. And we see that the tin has no coefficient in front of it because their coefficient in the balanced reaction is a 1. So we use the reciprocal of the coefficient from the balanced reaction as a coefficient in front of the rate change. So this means that the overall reaction rate would be half the rate of change for the iron with respect to time, or equal to the change of the tin with respect to time. And since the iron rate would be twice that of the tin, and then we take half of it, that would give us the exact same value. It's very confusing to hear verbally, but when you work it out in problems, you'll see that it turns out exactly the same. Now notice also that we've got a negative sign in front of the iron 3 plus and a negative sign in front of the tin 2 plus. This is because they are reactants, and so their rate would be negative. So by changing the sign of the negative rate, we give it a positive value, which would match exactly the positive values got from measuring the rate as an appearance of products. And so regardless of which of these components we measure the rate with, as long as we use one of these forms for the rate, we will always have the exact same value regardless of which reactant or product we choose. And so there again, we use the inverse ratio of the coefficients. Reactants always get a negative sign for their rate. Products will always have a positive sign. So let's consider a reaction. A plus 3B goes to 2C plus 2D. We're going to carry out a reaction and take some measurements here. So at time equals 2 minutes, we measured that the concentration of B was 0.9986 molar. And at time equal to 15.2 minutes, we measured the concentration of B at 0.9746 molar. We want to know what the average reaction rate was during this time. Okay, so let's just take a look at how we would express the rate in terms of all the different components. We don't have to do this for this problem, but this just kind of helps us see how to write these reaction rates. So we would write negative delta A over delta T, because the coefficient of A is 1. That's equal to negative 1/3 change in concentration of B over change in time. And again, that 1/3 because the B is a reactant and it has a coefficient of 3. So the reactant part is why we have that negative sign. When we look at C, we have plus 1/2 change in C over time. And for D, plus 1/2 change in D over time, change in time. So we use those 1/2 because the coefficient of C and D are 2. And we use the positives because they are products. Well, we're going to worry about B for this one. So let's go ahead and take a look at this calculation. The change in concentration of B is going to be your final concentration minus your initial concentration. So we have 0.9746 minus 0.9986. So notice that we get a negative change in the concentration of B. Well, that makes sense. B is a reactant, and so its concentration is going to be dropping. We look at the change in time. Our final time was 15.2 minutes. Our initial time was 2 minutes, and so the change in time was 13.2 minutes. Now, if we wrap that all up, we see that rate is equal to negative 1/3 change in B over change in time. So we're going to get negative 0.0240 molar over 13.2 minutes. And we get an average rate during that time of 6.06 times 10 to the minus 4 molarity per minute. Now, if I had measured the concentrations of A, C, or D and plugged them into the appropriate equation, I should have calculated the exact same rate for that reaction. Let's take a look at reaction conditions, because there are different things that can affect the rate of a reaction. Some we talked about. We did talk about concentration, temperature, we haven't talked about the presence of a catalyst yet. We're going to do that here in just a little bit, as well as the surface area of any solid reactants. So how does each of these affect the rate? Well, we talked very briefly about concentration and temperature. We're going to talk about that in a little bit more detail. So when we're looking at reaction rate and concentration, when we're dealing in the field of kinetics, what we're really trying to do is to establish some sort of mathematical connection between the concentration of your reactants and the rate of the reaction. And this equation has to be determined experimentally, and it's something that we call the rate law. Now, if we have just some generic reaction where we have A plus B going to C plus D, and let's say our coefficients for all those different reactant products are little a, little b, little c, and little d, we can write a generic rate law or a general rate law for that reaction, saying that rate is equal to K times the concentration of A raised to some power m times the concentration of B raised to some power n. Now that K that's there, this is called a rate constant. And the exponents that we have there, m and n, notice that they are not part of the overall reaction. M and n are two values that have to be determined experimentally. We call m and n reaction orders. Well, what is a reaction order? Well, again, they're orders, they're exponents that we use mathematically to enable us to calculate the rate of a reaction based upon concentration of our reactants. The overall reaction order of a reaction is just the sum of those exponents. So let's say m and n are both 1. So if we were to raise two concentrations to the power of 1, then the overall reaction order would be 2. If we had a concentration that was squared and something that was raised to the first power, then the overall order would be 3, 2 plus 1. Now again, we have that m and n, and they were not part of the overall balanced equation. What we have to do is we have to do a series of experiments to determine what effect each reactant has on the reaction rate. And once we do that, we can find what the exponents are for that rate law. And so these experiments have a related name. They are called rate law experiments. So in lecture 5, we started looking at reaction rates and what affects those rates, and now we're going to start taking a little more quantitative look at reactions and reaction rates and try to determine these reaction orders, these exponents that are part of the rate law. And so what we're going to do is these things called rate law experiments, where we're going to change the concentration of one of our components at a time to see what effect that particular reactant has on the rate of the experiment. So here's an example equation. We've got mercury chloride and the oxalate ion reacting to give us some chloride ion, carbon dioxide, and mercury chloride. A little different mercury chloride. And we can write just a general rate law for this reaction. We've got rate equals K times concentration of HgCl2 raised to some power m times concentration of the oxalate ion raised to some power n. Now we have no idea what those exponents m and n are just by looking at the balanced reaction, and so we're going to have to do a series of experiments to determine what those exponents are going to be. So here's a very typical set of data that we would get from a series of rate law experiments. We can see that in going from experiment 1 to experiment 2, we changed the concentration of the oxalate ion, and we can see that the rate changed. And then in going from experiment 2 to experiment 3, we see that the oxalate ion concentration is now the same, and we only changed the mercury chloride concentration. And again, we see an example of, we see the rate change there. So again, we're always comparing two experiments at a time, and we do this to see what effect did changing the concentration of only one reactant have on the rate. Now, in order to do that, we have a fairly easy equation that we can just plug in our values for. We're going to compare the rates to the ratios of the concentrations, and that ratio of concentrations is going to be raised to some exponent, and the exponent that we find for this equation is going to be the exponent that we plug in for that particular reactant. Now, I don't have this one worked out here. We will work it out in class. I will also put it up on D2L as a pencast. Let's talk about this rate constant K. What it is a proportionality constant, like so many constants are. Once we have a rate law with the orders plugged into the equation, we can then take any of our rate law our rate law equations, or our rate law reactions that we've done for that particular reaction, and solve for the value for K. Now, any single experiment's data can be used. K is not as constant as we think a lot of constants are. With K, it's very condition dependent, and it does change with temperature. So as soon as the temperature of a reaction changes, we do have to do a new series of experiments and find a new value for K. And the units of K change, and so what we need to do is to relate concentration and time, and so the units for K are different depending on the orders of the different reactions. We don't ordinarily really worry about the units for K for reasons that are beyond the scope of this course, but I'll never ask you for the units of K. The key with K is that the overall rate must come out to be units of molarity per time, since that's the rate. It's a change in molarity with a change in time, so the rate has to have units of molarity over time. Now, sometimes what we want to do with a reaction is determine the concentration of a particular reactant or a particular product at a very specified time during a reaction, and in order to do that, we need to use things that are called integrated rate laws. So what we're going to do is we're going to relate concentration to time, and the rate law equation, the integrated rate law equation, is dependent upon the overall order of the reaction. Remember that overall order is the sum of any of the exponents that we found for the orders. Let's look at a first order reaction first. So in a first order reaction, the reaction rate and the rate law is directly proportional to concentration, and we get an equation that looks something like this, where the change in R over the change in time, or the change in concentration of a reactant over the change in time, is equal to the rate constant found from the rate law times the concentration of R. And this can be transformed into what we call the integrated rate equation using calculus. We're not going to go through the derivation here. I believe your book does, if you want to take a look at it. But what we end up with here is that the natural log of concentration of some reactant at time t over the concentration of that reactant at time 0 is equal to negative kt, where k again is the rate constant and t is time. Okay, so again, this little 0 here indicates that we have a time of 0, and this little t here indicates some t, or some time t. It can be any time that we want it to be. But the t here is equal to the t there. So here's an example. So we have natural log of RT over R0 is equal to negative KT. Let's look at some mathematical things here. This value here, RT over R0, because they're reactants, this ratio will always be less than 1, because reactants, as the reaction proceeds, will always go down, which means the greatest concentration is always at time 0. So since concentration of R at time t is always less than concentration at time 0, this will always be less than 1, which means that this whole term with the natural log will always be negative. This is why we have the negative sign here, to make sure that we have a positive value for k, and we can only have a positive time t. Now, if k is known, we can figure out how much time is needed to reach a certain amount of product. If we know the amount of time, we can figure out how much product we would have at that time. So it's a fairly flexible equation, and we can use it for a variety of things. Now, for this particular equation, for first order, k is independent of concentration, and the units for k here are going to be time to the minus 1. So here's an example. We have hydrogen peroxide decomposing in a sodium hydroxide solution. It's a first order reaction, so we're told it's first order reaction, and we want to know what the concentration of the reactant hydrogen peroxide is after 100 minutes if the initial concentration is 0.020. We're given the rate law there, we're given the value for K, so all we need to find is the concentration of H2O2 after 100 minutes. Now, second order reactions, when we say second order, it means that the overall order of the reaction is second order, and we have two possibilities here. Either we have one reactant that is squared, so one reactant that's second order, or we have two reactants, each are first order. So two different ways we can do this. It does not affect the rate equation, and so your rate equation here is going to be negative change in reactant over change in time is going to be equal to K times concentration of that reactant squared. The integrated rate form, which is generally what we want to use, is that 1 over concentration of the reactant at time t minus 1 over concentration of that reactant at time 0 is equal to Kt. Again, since concentration of reactant at time t is smaller, this will be a larger fraction than this one, and so we always get a positive value over here. The units of K in this case are liter per mole time. Here's another example. Here we have a gas phase decomposition of HI. We know it follows a second order reaction, so we want to know now how much time does it take for the concentration of HI to drop from 0.010 to 0.0050. So we want to cut the concentration of HI in half at 443 degrees Celsius, and we're given the K value here. Now, zero order reactions are a little bit of an unusual type of reaction. So here the rate of reaction is completely independent of reactant concentrations. It means I have no exponents for any of the reactants. And so our rate equation here is negative delta R over delta T is equal to K times concentration of reactant raised to the 0 power. Well, anything raised to the 0 power is a value of 1, and so we have K times 1. So the rate of the reaction is dependent only on the rate constant K. And the integrated rate equation here is concentration of the reactant at time 0 minus the concentration of the reactant at time t is equal to Kt. And the units of K are molarity times time. That's not a minus sign, it's just a separator. And the first thing we're going to talk about is half-life. And this is a kinetics related topic. And the half-life of a reaction is really just the time it takes for a reaction to have its reactants to reduce their concentration by half. And it doesn't really matter where in the reaction it is. Just from wherever you start to wherever you finish, the reactants will be cut in half. We very frequently use the starting point, but it doesn't necessarily have to be the starting point. So we see half-life indicated by T with a little subscript of a 1/2 to indicate half-time or half-life. And primarily we use it for first order reactions. We certainly can use it for zero order and second order. Our book talks about half-life for zero and second order as well as first order. We're going to focus primarily just on first order. Now, when we're looking at an integrated rate equation graph that we saw in lecture 6, we have that nice straight line where we have the natural log of our concentrations on the y and time on the x, and we can find our half-life anywhere on that first order graph. So we don't have to start at the beginning. We can look anywhere on our graph to find the half-life. The reason we can do that is because the half-life of a first order reaction is independent of concentration. It's dependent solely on K. And so there's our equation there. We have our half-life, which is equal to 0.693, which is actually the natural log of 2 over K. And so we see there that the concentrations of the reactants don't factor into the calculation for half-life at all. It's based solely on the rate constant, and as long as we keep our temperature the same, the rate constant remains the same, which means our half-life will remain the same. We can look at a graph of concentration versus time if we want, and there we see if we start at time 0 up here, we have a concentration of 1 molar, and so when we get to half molar, the time it takes to cut that concentration as half is the half-life. And so we see here it took 100 seconds in order to cut our concentration to 0.5, so our half-life would be 100 seconds. And what that means is that every 100 seconds the concentration is cut in half. So we went from 1 to 5, and then we go from 5 down to 0.25, from 0.25 down to 12.5 or 0.125, etc. And it wouldn't matter where we start. If we look at the time at 0.75 here and went down to 0.375, we would see that would also take 100 seconds. So it doesn't matter what the concentration is to start. It's going to take 100 seconds in this case to go to half of whatever your starting concentration happens to be. Well, here's an example that will work out in class. It says for the decomposition of N2O5, the rate constant K is 1.7 times 10 to the minus 3 inverse seconds. How long will it take for a sample to decompose to 12.5% of its original value? And there's our reaction there, which isn't terribly important. But again, we will work this one out in class. So also related to kinetics is a thing called the Arrhenius equation, put forth by Svante Arrhenius. And what it really does is it relates reaction rates to inherent factors in the reaction. These are things that you can't really change. So we have the energy in the reaction, the collision frequency, the collision geometry, and the activation energy of the reaction. And here is the equation that relates all of those things together. We have K, which is the rate constant. So K is equal to this capital A, sometimes called an Arrhenius factor or a frequency factor. Sometimes it's called a pre-exponential. It has a lot of names. It's all the same thing. And then we have this large exponential term there. So we have e to the minus EA over RT, where EA is our activation energy, R is our regular gas constant, but this is going to be the 8.314 version since that uses energy, and then T, of course, is temperature in Kelvin. And so that exponential term really represents the fraction of molecules that have the minimum amount of energy needed in order to react. And got a little funny saying there in your face. Svante Arrhenius is an interesting historical character in terms of chemistry, and we'll talk about him in class just a little bit. Now, what is that term, that exponential term? Where does it really come from? Well, it has to deal with temperature and the energy in the collisions. So temperature is a measure of kinetic energy. It's not a measure of heat. And so if we think about temperature, or kinetic energy rather, kinetic energy is made up of mass and velocity. And so as I increase the temperature or decrease the temperature, really the only thing that can change there is the velocity. I can't change the mass of a material by changing its temperature, but I can change its velocity. So what that means is that raising the temperature of a sample causes those molecules to move faster, and or vice versa. Adding heat causes those molecules to move faster, and that in turn causes the temperature to rise. So as those molecules move faster, they collide more often, and they collide with more energy, and so the reaction rate will go up. Now if we look at this little graph here over here on the side, so our EA there, some activation energy, which is an energy barrier really that molecules have to be able to meet in order to react. Now, this exponential for this fraction of molecules with a certain energy never goes to zero. So even if you have a really high activation energy, there's always going to be some small fraction of molecules that have enough energy. So you're always going to have a little bit of a reaction. But here in blue, we see this graph right here, and we see that there's only a small fraction of those molecules that have enough energy to get up and over that activation energy barrier. So the reaction rate will be sort of slow. Now if we look at temperature 2 shown in red, and it's in red because it's a warmer temperature than temperature 1, we see it here, and we see that the area of temperature 2 that goes above the activation energy is quite a bit higher than that of temperature 1. And so more molecules at the higher temperature have enough energy to get over that activation energy barrier, and as a result you're going to have a faster rate. So let's talk about activation energy in a little bit more detail here. As I mentioned, activation energy is this minimum amount of energy needed in a collision in order for molecules to react, and we indicate that by an E for energy and a little A for activation, so activation energy. Different types of reactions have different types of energy barriers, different activation energies. If there's a low energy barrier, that's going to mean that a lot of molecules are going to have enough energy to get up and over that barrier. So as a result, you're going to have a fairly fast rate. If you have a high energy barrier, well, that's going to mean that not very many molecules have enough energy, and you're going to have a very slow rate. And we describe these rates in a reaction coordinate diagram, which is going to show our energies both for the reactants and for the products, and then show graphically also this barrier that these molecules have to get up and over. And we'll take a look at that in this next slide. So RC stands for reaction coordinate, and if we look at it, this isn't a very quantitative graph, which is fine. Sometimes you'll see the energies for both the reactants and the products. You might see them listed over here on the y-axis. But reaction progress, you never really see. It doesn't necessarily indicate time. We don't use it as a quantitative measure of time, just reaction progress. So we pretty much go from reactants here to products here, and that's the end. However long that happens to be, it doesn't really matter. We're just looking at reactants to products. But this RC diagram does indicate where energies lie during the progress of a reaction. It shows the highest energy point during a reaction, which is going to be right up in here. And that's where we've got those bonds starting to break and starting to form during a reaction. Very high energy, well, it's the highest energy in that reaction, and the species that exists at that top energy has a couple of names. Sometimes it's called an activated complex, and sometimes you hear it called a transition state. So I'll generally refer to it as a transition state. It's that transition from reactants to products. So the energy from the reactants to the transition state is the energy for the activation energy. So we see that right here, our blue arrow going from the energy of the reactants up to this top hill. So the difference in those energies is going to be our activation energy. So how do we arrange all of this into the Arrhenius equation? Well, the Arrhenius equation has a couple of different forms. We're going to look at both of those. Mainly what we want to do with that Arrhenius equation is to rearrange it into a linear form, because linear forms just tend to be a little bit easier to work with. And it will also allow us to solve for the activation energy of a reaction. So here we have the Arrhenius equation arranged into a linear form. It's had a little bit of math done to it. But we have natural log of k, so our rate constant is going to be equal to negative EA over R times 1 over T plus the natural log of the frequency factor there. So that in essence is the Arrhenius equation. That's the linear form of the Arrhenius equation. We see the comparison down there below, how it lines up to a straight line. So if we graph the natural log of k on the y-axis and what do we got on the x-axis? 1 over t in Kelvin, then our slope is going to be negative EA over R. And so we can find our activation energy from the slope of that line. Now, one of the issues that you can have with that form of the Arrhenius equation is finding what that frequency factor is. And we can eliminate that frequency factor by taking a look at two temperatures and using a two-temperature form of the Arrhenius equation. And I'm not going to derive that out here. I believe it's done in your book. Or if you would just like to see how we go from a single temperature version to a two-temperature version, you can certainly come to my office hours and we can take a look at that. But here's the two-temperature version. We have natural log of K2 over K1, so that's going to be the rate constant at temperature 2 over the rate constant at temperature 1. And that's equal to negative EA over R times, and we've got 1 over T2 minus 1 over T1. Now this form of the equation is just slightly different from the one that you have in your text. The version in your text actually swaps out T2 and T1 here and gets rid of that negative sign. I don't like that form as much. To me, this one is a little bit easier to remember because the K's and the T's sound like they're in the same order. You have K2 over K1 and T2 minus T1. To me, that's just easier to remember, so that's why I like this version a little bit better. Either of them will work. Mathematically, they're identical. But when I teach it, I like to teach the K2 over K1, and then inside those brackets, T2 minus T1. They're easy to confuse, so you want to make sure that you get them in the right order. Well, here's an example of a two-temperature version. Here we have a rate constant for a reaction at 298 K, and what we want to know is what's the rate constant at 350 K, and we're given the activation energy. Any of those variables in that two-temperature version of the Arrhenius equation could be solved for. Here we're solving for second rate constant. We could have solved for second temperature if we wanted a certain ratio of rate constants. We could solve for the activation energy if we knew everything else. So just a lot of different options for what we want to solve for. But we'll work this one out in class. Now we're going to shift gears a little bit in our discussion on kinetics, and we're going to start talking about reaction mechanisms. Reaction mechanisms is really how reactants move from reactants to products. So let's take a look at this reaction here. This is just cellular respiration. We've got glucose there, C6H12O6, plus 6 oxygen molecules. It's going to end up giving us 6 carbon dioxides and 6 waters. Now this really is not likely to occur in a single collision. We would need to have the glucose molecule and all 6 oxygen molecules collide with the proper energy, with the proper geometry for all 7 of those things. So the likelihood is just really low, and if our lives depended on that collision happening, we probably would not be alive. So instead what happens is generally a series of small steps, simple two-bodied collisions, and we call these small steps elementary steps. So we generally have two molecules colliding. Occasionally we'll have three molecules colliding, but we always try to work it with two, because two things running into each other is much more likely than three things running into each other, because the collision for three things would have to be those three things meeting at the same time, at the same point in space, with the proper geometry. So we link together a series of these steps, and we show exactly how reactant molecules become products through this series of steps, and this is what we call a reaction mechanism. So here's just a simple version of a single step mechanism. We have A2 plus B2 going to 2AB. We have the collision there between the A2 and B2 molecule. They break the AA bond, the BB bond, and they form two new AB bonds. So that would be a single step mechanism. Here's another version of that exact same reaction shown in three steps. So we have two A2 molecules running into each other. One of the A2s break apart. One of the A atoms then grabs onto a B2 molecule, making an AB2 species. That AB2 reacts with the other A that was formed in step 1 and forms 2AB. So there we see two different versions. We see a one-step mechanism and a multi-step mechanism. I start off talking about rate laws and elementary steps. So elementary steps are things that can help us find a rate law, and vice versa. A rate law can help us determine an elementary step in a mechanism. Now, when we have a mechanism, a proposed mechanism, we can write a rate law for each individual step in that mechanism, and we can do that directly from the coefficients for the different reactants in that step. This is not something that we can do for an overall reaction, but we can do it for an elementary step. Let's take a look at some examples here. So we're going to assume that these following reactions are just elementary steps within a mechanism. This is not just a mechanism, these are just individual steps from different mechanisms. So for that first one, where we have A going to B, we would write the rate law for that step as rate equals K times concentration of A. For A plus B going to C, we would write rate equals A, K times concentration of A times concentration of B. Again, because A and B are reactants, they have no exponents because the coefficients for A and B are 1. So technically the coefficients for the concentrations of A and B are also 1. And then for that third one, where we have 2A going to B, we say that the rate is equal to K times concentration of A squared. And again, that one is squared because of the 2 here that corresponds to that exponent there. Again, we can only do that for elementary steps. We cannot do it for an overall balanced reaction. So just to reiterate that there, rate laws can be written for each step in a mechanism directly from the coefficients of the reactants in those individual steps. But again, cannot do this from an overall balanced reaction. So you want to make sure you don't get into that habit. Let's take a look at a reaction here. We have 2NO plus O2 going to 2NO2. Now we see that we've got just three bodies in the reactants, 3 molecules there. So it is possible that it's a single step reaction. However, it's not very likely, just because that would mean that we'd have a 3-bodied collision leading to products. It is possible. That does happen, but it's not the likeliest circumstance. Now let's say also that we have a little bit of some experimental data, and during the course of the reaction, the species N2O2 is detected during the reaction. Well, if it were a single-step reaction, then we would never see this species N2O2. We would only see NO, O2, and NO2. So since we see N2O2, that means our single-step possibility is gone, and we have to start from scratch, and we have to build a multi-step mechanism. So let's just take a guess at a two-step mechanism, and we'll use what we know. The only thing that we really know is that we have N2O2 serving as a reaction intermediate here. So we're going to have two of our reactant molecules from the reaction, our two NO molecules. They're going to collide and kind of fuse together and make an N2O2 molecule. Then that N2O2 molecule is going to react with the other reactant, O2, and that'll give us 2NO2. Notice that both of these steps in the mechanism are balanced, and that's very important. Your individual elementary steps do also have to be balanced reactions in and of themselves. Now, to make sure that this mechanism adds up to the overall reaction, if there's anything in the products and in the reactants, it's something that we can cancel out. So here we see we have N2O2 in the products of the first step, and we have N2O2 in the reactants of the second step, and so those cancel out, and what we're left with is 2NO plus O2 going to 2NO2. So here the elementary steps add up to the overall reaction, and that is something that must happen. The sum of your elementary steps has to be equal to the overall reaction, and it has to be balanced as well. Notice also we saw N2O2 appears and disappears during the course of the mechanism, and when that's the case, we have something that's called a reaction intermediate. So it has to happen in that order. Something appears as a product and then disappears as it gets consumed as a reactant. That's what we call a reaction intermediate. So we have a reaction intermediate, N2O2. This was something that was observed experimentally. Our mechanism adds up to the overall balanced reaction, which means that this mechanism is possible. It's not necessarily correct, but it's not wrong yet. So we would have to do more studies to prove that this mechanism is correct. However, at this point, it's still a possibility. Now, when we create a mechanism, there are two conditions that have to be met in order to make it a possibility, and we just saw those in this mechanism there. The sum of the steps have to match the overall balanced reaction. That's important that the sum is balanced. So once you add up those steps, you have to get the overall balanced reaction. And the rate law for one of those steps in the mechanism, remember you can write a rate law for each individual step, but one of those rate laws has to match the experimentally determined rate law. Now the step that does that is going to be the slow step in the reaction mechanism, and we're going to call that the rate determining step. The reason it matches the rate law for the overall reaction that you find experimentally is because that one step determines the rate for the entire reaction. Let's explore these reaction intermediates just a little bit more detail here. These are species, as we saw, that appear first in a mechanism and then they disappear. So they're generally a very high energy species. Usually that means that they're going to be very unstable. Species that are unstable tend to be very reactive. Because they're very reactive, they react very quickly with other things in the reaction mixture, which makes them very short-lived. Because they're short-lived, they can be very difficult to detect. If you find a reaction intermediate that supports a mechanism, that's really good. Just because you didn't find it doesn't mean that your mechanism is wrong. It just may mean that you can't detect those reaction intermediates. So a little bit of a double-edged sword there. But they can support or disprove a proposed mechanism. So again, we saw that if your mechanism has a particular reaction intermediate in there, and you find that intermediate that lends support to your mechanism, if you find a species during the course of a reaction that is not predicted by your mechanism, then your mechanism is no good and you need to start from square one. So let's talk about what equilibrium is and how we study it, how we understand it, and ways that we can actually manipulate it. So if you go back and look at a lot of the reactions that you've done up to this point in both semesters that you've had of chemistry so far, you'll notice that a lot of times we draw our arrow for our reaction in a single direction. Well, as it turns out, very few reactions only go in one single direction, and we saw a little bit of that here in this last lecture in kinetics. What we can also see is collisions between product molecules that can recreate reactants, and so products re-react and form reactants all over again. So as a reaction moves in the forward direction, well, what happens to that? So if we start with just reactants and move a reaction in the forward direction, what we get is those reactants reacting, forming products, and as a result we have fewer reactant molecules present, and so as we've seen, that forward reaction rate slows down. But as that forward reaction rate slows down, because of fewer reactant molecules, what we're making is product molecules, and so we're increasing the number of product molecules, and as a result the reverse reaction rate begins to increase. So we have the forward rate decreasing and the reverse reaction rate increasing. At some point during that reaction, the forward rate and the reverse rate will be equal, and the reaction will have reached a state of what's called dynamic equilibrium. Now at that point, the concentrations have stopped changing, but that doesn't mean that the reaction has stopped. The molecules have not stopped moving around, they have not stopped reacting. It just means that the concentrations have stopped changing. Now, when we see this, the term equilibrium, one of the common misconceptions people think is that the concentrations of products and reactants are equal, and that just isn't true. The equilibrium is referring to the reaction rates, and the reaction rates are equal both in the forward and the reverse direction. So when we write that a system is in an equilibrium state, we indicate that with a forward and reverse arrow, as we see here with A and C. And so forward and reverse arrow. If we want to see how equilibrium is expressed mathematically, we can do that using what we've learned from our kinetics chapter. We know that for equilibrium to be reached, we have to have the forward rate equal to the reverse rate. So we say rate forward is equal to rate reverse. Well, we learned how to express the rate in terms of the rate constant and concentration, and here we're going to use our just an example reaction of A turning into C, that reaction in equilibrium. So the forward rate can be expressed as the forward rate constant, K forward, times the concentration of A, and the reverse rate constant, or it's going to be equal to the reverse rate, which is equal to the reverse rate constant, K reverse, times concentration of C. Well, let's rearrange that and put all of our rate constants on one side and our concentrations on the other. So we have K forward over K reverse is equal to concentration of C over the concentration of A. Now we see that we've got two rate constants there, K forward and K reverse, and so K divided by AK is going to lead to another K. One constant divided by another constant gives you yet another constant. So that value is in fact a constant. And those concentrations for C and A are going to be equilibrium concentrations. These are not initial concentrations where the reaction started. These are going to be equilibrium concentrations where the reaction has finished up when it reaches equilibrium. Well, we're going to call that ratio of the forward rate to the reverse rate K equilibrium. And notice that it's a capital K, and we have a little EQ down there to indicate equilibrium. As the semester goes on, we'll have several different equilibrium constants, but they all follow the same basic premise. We're going to have products over reactants. Okay, so here we have C over A. It was A turning into C. So it's a concentration of products over concentrations of reactants. It'll get a little more complicated than that, but not by much. Let's look at a little bit more complicated reaction here. It's still generic. So we have A plus B going to C plus D. And our small a's, b's, c's, and d's, those are just our stoichiometric coefficients from the balanced reaction. So for a balanced reaction, we can write our equilibrium constant expression directly, which is very much different from what we learned in kinetics. But for equilibrium, we can do this. So the equilibrium constant, KEQ, is equal to products over reactants. And so we have the concentration of component C raised to the power of its stoichiometric coefficient from the balanced reaction, so little c. And then we have times concentration of D raised to the little d. So it's my products over my reactants. So we have concentration of A raised to little a times concentration of B raised to the little b. Let's look at it for an actual chemical reaction here. We've got N2O4 in equilibrium of two NO2s. So products over reactants. So we have KEQ is equal to concentration of NO2 squared over concentration of N2O4. It's just that easy. Now the equilibrium concentrations are very important. They can vary within a single reaction depending on what starting concentrations were, but the most important thing about equilibrium is that that ratio must always hold true. And so here's a table for the reaction H2 plus I2 goes to 2HI. And we have our equilibrium constant expression there. It's going to be concentration of HI squared over concentration of H2 times concentration of I2. Now notice here we have several different types of initial concentration situations and different equilibrium concentrations as well. So in this first reaction, both H2 and I2 started at half molar. They finished at certain equilibrium concentrations, and what we find is that the ratio of those, when plugged into the equilibrium expression, we have an equilibrium constant of 50. Now, in the next one, we started with no H2, no I2, and half a mole or half molar HI. We find a very different set of concentrations at equilibrium for the H2, I2, and HI, and yet we still end up with an equilibrium constant of 50. On the third example, we have half molar concentrations of all species, and we have different values for the equilibrium concentrations again, but once again, those concentrations plugged into the equilibrium constant expression gives us a ratio of 50. So this value must be met, and that gives us a lot of power when we're looking at equilibrium constant expressions, the equilibrium constants, and what we can relate to them. And we'll see this as we move along, how it can help us. What does the value of that equilibrium constant tell us? Well, we can have it tell us where that equilibrium lies. What can I expect to find inside my reaction vessel once that reaction reaches equilibrium? So if the equilibrium constant K is much larger than 1, and here's an example of ozone turning into oxygen, it's got an equilibrium constant of 2.54 times 10 to the 12th, that's a lot larger than 1. What we're going to find in the reaction vessel at equilibrium is a lot more product than reactant. So for this type of reaction, we would say that the reaction favors the products. If K is much smaller than 1, so here's an example where we have a chlorine molecule breaking apart into 2 chlorine atoms, has an equilibrium constant of 1.4 times 10 to the minus 38. Very, very tiny number. What this means is the reaction really doesn't like to happen, and you have very little product form. So for this reaction, we would say that it favors the reactants. If a K is in the vicinity of 1, then what you're going to have left is a mixture of reactants and products present, and neither products nor reactants are favored in this case. And again, at equilibrium, you're going to have a mixture of both reactants and products, and you're going to have substantial amounts of both of those. Now there are some special cases when we're writing equilibrium constants, and we've talked about these just a little bit. I'll reiterate them here. So anytime we have a reaction that involves pure liquids, especially water, it seems to show up a lot in these reactions, or if we have a pure solid indicated by an S in our reaction,
we leave those out of our equilibrium constant expressions. Now the reason for this is that these two phases compress very little with a change in pressure or even with a change in temperature. So the concentration of a pure liquid or a pure solid is generally based on the material's density. That determines the number of moles in a certain volume of a substance, and so because that's a constant value, we work that constant into the equilibrium constant already, and we don't have to worry about it. So when we are writing our equilibrium constant expression, we leave out any liquids and any solids. Let's take a look at some examples of that. So here we've got acetic acid and water dissociating into the acetate ion and hydronium ion. And when we write the equilibrium constant expression, we just have products over reactants. But notice that we have left out the value for the concentration of water. Concentration of water is a constant. It's somewhere in the range of 55. And so that's already worked into the value for Kc. And so we can leave it out of the equilibrium constant expression. Let's look at another one here. So the decomposition of calcium carbonate solid, it decomposes into calcium oxide solid and carbon dioxide gas. And again, when we write the Kc here, it's just the concentration of CO2. We've left out the calcium carbonate and the calcium oxide because those are solids. That means their concentrations don't change and their values are already worked into the value for Kc. An important concept in equilibrium chemistry is this idea of a reaction quotient, and we just call that QC. You could call it QP if we're calculating for gases. It's very similar to the Kc. The only difference is that when we're calculating an equilibrium constant value, Kc, we're assuming that the concentrations we're using are equilibrium concentrations. When we're doing a QC, we don't make that assumption. So we just use the concentrations at hand, and then we can use that value to determine if the reaction is at equilibrium or if it has to shift more to the right to get to equilibrium or to the left to get to equilibrium. So we can use the value of Kc to determine which direction that reaction has to move to reach equilibrium. Well, let's look at a reaction here, H2 plus I2 going to 2HI. We would write an equilibrium constant expression here as Kc is equal to Hi squared over H2 times I2. And again, because this is an equilibrium constant expression, we are assuming that those concentrations there are equilibrium concentrations. We write our Qc expression in the exact same way. The only difference is the concentrations there don't have to be equilibrium concentrations. They can be any concentrations at any time t. And then we're going to compare the value that we get for Qc with the value we get for Kc. So let's take a look and see how we do that. So if we calculate a value for Qc and it's greater than Kc, that indicates that the products in the numerator are more abundant than they should be at equilibrium. And that means that the reaction needs to move towards the reactants, or it needs to move to the left in order to reach equilibrium. Vice versa, if Qc is less than Qc, that means the reactants are more abundant than they will be at equilibrium, or you can think of it as we don't have enough product than we should to reach equilibrium. And so that means that the reaction is still moving in the forward direction in order to reach equilibrium. So we would say that that reaction is shifting right. And if we find that our value for Qc is equal to Kc, well, that means that our concentrations are in fact equilibrium concentrations and the reaction is at equilibrium. Let's look at an example using our H2, I2, and Hi system there. So we have a Kc value for this reaction at 54.3. It's something that we would look up. And so we have this reaction taking place. We took a sample from this reaction and analyzed it, and we found the following concentrations. So what we want to know is the reaction at equilibrium? And if it's not at equilibrium, which way does it need to shift to reach equilibrium? Or you could say, which way does it still need to proceed to get to equilibrium? Well, let's find a value for Qc. We know the value for Kc. So we see we have Hi squared over H2 times I2. Plug in our values that we found, and we find a Qc of 111. Now, a value of 111 is greater than the equilibrium constant, so this reaction has too many products, and as a result, we have to the reaction is going to be moving to the left. So you're going to have more collisions of product reforming reactant here in order to reach equilibrium.
And what Le Chatelier's principle covers is a general rule looking at how a reaction will respond in order to restore equilibrium after a disturbance throws a reaction out of equilibrium. So let's take a look at some of the different ways that we can disturb an equilibrium. We can change the concentration of a component. So if we can imagine a reaction that's at equilibrium, and perhaps we add something more to the reaction, or maybe we take something away, how will that reaction respond? If we have a reaction that takes place in the gas phase, either a pressure or volume change can certainly impact where the equilibrium lies for that particular reaction. Or we can certainly change the temperature of a reaction, and when we change the temperature, it affects a lot of different things, and one of the things it might affect is the position of equilibrium for a reaction as well. So if we state Le Chatelier's principle in a very simple manner, we just say that if an external stress is applied to a system that's at equilibrium, the system will adjust or shift to partially offset that stress and restore equilibrium. Let's take a look at concentration changes first. So let's consider this reaction at equilibrium. So we've got iron thiocyanate, which is a red color, iron 3 plus yellow, and the thiocyanate ion colorless. So that reaction there is in equilibrium. It's got a Kc as we see there, iron 3 plus times SCN minus over the iron thiocyanate complex. Now let's say that we've got this mixture at equilibrium and we add some sodium thiocyanate. Now sodium thiocyanate is a salt. It's going to be a soluble salt since it's a sodium salt and will readily dissolve in water. And when it dissolves in water, we add, in essence, some thiocyanate ion there. And what we find is that this concentration turns more red than it was before. Well, why was that? Well, we've increased the thiocyanate ion. The solution was at equilibrium. We've now increased the thiocyanate ion concentration, and in doing so, we've taken that reaction out of equilibrium. So we've disturbed the equilibrium. At this point, the reaction has too many products. The thiocyanate has increased the amount of products. So this means that the rate of the reverse reaction has increased, and that means that the reaction will shift back to the left or towards the reactants in order to restore that equilibrium. So in shifting to the reactants, we're shifting towards that red complex, and the solution turns more red. Let's take a look at another example here. So the reaction of iron 3 oxide with carbon monoxide is used to reduce iron ore to iron metal. So this is one of the ways that we get iron metal from our metal plants. So we've got iron oxide there, iron 3 oxide, reacting with 3 carbon monoxide gas, and we get iron liquid and CO2 gas. So what we want to do is use Le Chatelier's principle to predict the direction of the reaction following these disturbances. So let's say that we remove carbon dioxide. And I've got these little graphics on here. Hopefully they'll help with the visual here. So we're going to remove CO2. So we are removing a product. Now in our little graphic there, we can imagine the removal of something as a down arrow on that side, and it's going to tip our teeter-totter, and what we want to see is what ways the ball is going to shift. So we shift that down and the balls move to the right, and that indicates that our reaction will shift to the right. By removing a product, the reaction is going to shift in a direction to replace that product, and that means shifting to the products to replace the CO2 that we've removed. What if we remove carbon monoxide, something in the
reactants. Well, in the reactants, so we're removing something, so again we're going to use a down arrow, only this time, since we're removing a reactant, we're going to put that down arrow on the left-hand side. And we see when we move that down, the balls shift towards the left-hand side. So again, when we remove something, the reaction wants to shift in a direction that will replace it. So by removing a reactant, we're going to have a slower forward reaction, and the reverse reaction is going to be faster now, and it's going to try to replace what was removed from that reaction. So here the reaction would shift to the left or shift towards the reactants. Now this one's a little bit tricky, adding iron oxide. And you'll notice that I don't have my little teeter-totter there. Well, if we look at the state of iron oxide there, we see that it's a solid. Now remember, solids are not included in the equilibrium constant expression, and if they're not part of the equilibrium constant expression, then adding or removing those components is not going to affect the position of equilibrium. So it also does not apply when we apply Le Chatelier's principle to the removal or addition of the Fe2O3. The same would also be true as if we removed iron liquid. It just doesn't affect the position of equilibrium because it's not part of the equilibrium constant expression.